Hi guys, I'm Łukasz. I'm lead Gen AI engineer that specializes in inference. Today we'll look how to shrink the model as much as possible while retaining the precision. And this will turn out into having model that performs really fast with the same quality of output or into complete garbage. And it all depends on one decision. We'll look into the types like FP32, FP16, FP8, INT4. So after this, you will understand all of the concepts related to it and also how to benchmark it to understand if what we are doing even makes sense. And you will know how to run the model on your GPU, and you don't need to randomly choose which one to run and so on. So let's dive in. So in this local AI series, we'll look into FP16, FP8, and INT4. And by the end, you will understand exactly what quantization is, even if you are not an AI expert. So what we'll cover, there will be 5 quick parts. Why models are big, when you are even allowed to lower the precision, what quantization actually does to the numbers, how we check whether we broke anything. And then in this 4 lineup, I will save running it in production and comparing it on the next video. So a quick shout out to Summerose, because while creating this video, I look for how to create really good visualizations, and I found this blog and it have everything I need to explain things there. So I will use a lot of references from this blog. So why are models so big? It comes down to how many numbers a model stores and how each one is written down. Now let's look at the model. So the large language models contains billions of numbers. And what are these numbers? Here we can see simplification. We have inputs, we have weights. Each of them are some number. Then we multiply the input by the weight. We get the layers inside. And then after a few columns or thousands of columns, we multiply again what we get with weights, and we get the output as a sum. We can picture it as a value knob. It decides how loudly the signal that we feed, for example, from this layer will impact the output. And a mid-sized model can have 9 billion of them, and every single one has to be stored. That storage bill is the entire reason quantization exists. So the real question becomes, do we actually need to write down every one of those numbers at full precision? And here we can see example with some numbers. So again, we'll start over with simple one. So the input is 1, and then we go through this weight. So we multiply 1 by 0.1, 0.5, 1.5, and this gives us the layers that are here. So 0.1 again, and so on. Then we need to multiply these values by the weight. So we multiply 0.1 by 0.1, then 0.5 by 1, and 1.5 by 0.5. That gives us 1.3. Well, actually no, that will give us a bit smaller value, but because as we see we have only one place after the dot, we will round it because it will be around 1.26. And now we can see what will happen if we change it. If we change it to half, we can see that it impacts the output here. And if I increase it to 2, then it will impact the weight. So we have 2.5 here, and on 1 we have 1.3. So we see there is some rounding here. Then when we go to the maximum, we can see what's gonna happen with the results on the output. And now we'll jump to a bigger example. So here we can see we have 2 inputs, and we go through the layer, we apply weights again, we go through the layer, we sum all of the values that goes as a input on the layer here, then we get 2 outputs. So as you can see, this could get quite complex. And now imagine billions of them and trying to analyze what it actually means. That's why we still don't really know how all of this work, where all of this knowledge from the models came from, or the prediction of tokens. So that's like a field of explainable AI that still try to find out how the old algorithm works where we develop the newest one already. The storage bill is the entire reason quantization exists. So the real question becomes, do we actually need to write down every one of those numbers at full precision? So before we jump into it, there is question that maybe you wanted to answer. For example, how do we write down these numbers? Because I showed a really simple example. First, we'll look into this schema. So a floating point number, which is most commonly used, consists of three parts: the plus or minus sign, the exponent, so how big or small the range will be, and then the significand, how many digits of the detail we keep. So integers skip the exponent entirely. They are just evenly spaced buckets. So hang on that distinction, because later we'll see the reason that FP8 and INT8 behave nothing alike, even in the same number of bits. Okay, so here we have the example of unassigned int8. So it's unassigned because we don't have the sign bit, as we can see here. And here we have the values, because bits consist of 1 or 0. And if we, for example, want to make 1, we change this bit and we'll get the 1 as a result. But what if we want to do 2? You will think we just do this. But no, this will give us 3 because we do summarization of all of these values here. So if I want to do 2, just need to only choose this bit as 1. And then to show how it goes, we can do 3, then 4, then 5, 6, 7. So as you see, there is pattern. We mark the highest bit that consists of the value that we can fit. So in this case, 8. And then if we want to do 9, then I need to mark this. And then if I want to do 10, I can do it with just these two. And if I want to do 11, then I do this, and so on. Now, if I, for example, want to do 12, then I can just do this. So now let's quickly look how it goes. So as you can see, we are picking the highest bit, and then we choose the ones from the lower range. So this is like a pattern that repeats if you work on this long enough. And as we can see, the maximum value is 155 plus 0, which is 256 altogether. Now we'll look into the formula for the more complex example, but this was to give you kind of feeling how it works. Okay, so now we saw simple examples. So now let's look at the bit more complex one. So we have one formula that ties the three fields together: the sign bit that flips it, the exponent that scales it, and the significand that fills the details. It's also named mantissa. So as we can see, the exponent scales the value by power of 2, but it's stored with a bias of 127. This is because we want to represent the negative and positive values, so we move all the range. So 127 is in the middle from 255. So then when we store the value, the real value will be when we subtract this, because we move the scale by 127. So if from the bits we have 137, then we subtract and we get 10 to this formula. And then we have significand or mantissa. So this is just a fraction, a half, a quarter, an eighth added on top of leading one. It flips the bits and we can dial the exact number then to the formula. And of course, we add the fraction when it's one value. Now let's look at the example that we'll also then look later. So here we have the exponent, the significand, and sign bit. So first, through the sign bit, we have 0. So this will be positive value from the formula that we have here. So we can say it's -1 to sign bit. So sign bit is 0, so -1 to 0 is +1. Then we have exponent. So we have 127, and as I explained before, we subtract 127. So this actually represents 0. So then looking at our formula, we will have 2 to 0, which is 1. And then we have a significand. So we can check here. We have 1 here. Now, if we look at the formula, here we just put the full number as bits. So we'll add 1, and it's 1.1, but it's a bit scale with a base 2, so it's 1.5. So then it's 1.5 plus 1 multiplied by 1 from all of this, which give us 1.5. Now we'll look into better animation. So here, if you want to practice, we have the same example as I just showed you. And as you can see, we can change the significant, add values here, and basically play with it. And for example, what I don't show is we can add the sign bit and change the values. And as you see, sometimes the value will jump. For example, here, you see we have 477, 596. So this is the precision, compromise, because we, even with this float, can't express every possible number, And here we have the distribution of 32-bit float values. We have the value range here and then unique values in a range. And as you can see, there is big peak around 0. There is over 2 billion of values here, which accounts for over 39%. So this is in logarithmic scale, And then we can change it to linear or like to percentage also. So then it's like this. So why it's important? A lot of the representable 32-bit floats are small values, and this is fantastic for LLMs because parameters also tend to be small, and small parameters have been found to result in model that generalize better to problems they haven't seen before. So the models are rewarded during training for making parameters small. So that's like how it works in LLMs. And here we'll look into another histogram. So it was created again by the author of the blog by 6 popular open source models, and we can count the parameters here. And as we can see here, the distribution of model parameter values, we have Quencoder, DeepSeek, GLM, Voxtral, GPTOSS, and so on. And as we can see on the x-axis, we have parameters value range and then percentage of parameters in that range. And maybe let's look at the top. So as we can see, the majority of parameters are in the middle, so really close to 0 range. So it's from minus 0.005 to 0.005. And here we can also play with range, to see it. But the default option was basically best. And we can do it by percentage or absolute value. So most model parameters sit in the range of floats that can be most precisely represented. So this will be very important when we also jump to it later. So now let's jump to the formats guide, and as we can see, every format gets a fixed bit budget, and we can watch here where this bit budget is spent. For example, we have the full precision with 8 exponent bits and 23 significand. Then we have half precision, which is FP16, BF16. As we can see, there is difference. We'll explain it on the example, so it's easier to understand. And then we have FP8, which is a tiny float. It's coarse but flexible. It's commonly used in VLLM engine for the inference because it provides good results with reduced VRAM and a bit speed up in the token. And then we have INT8. So here, as we see, it's changed. We have levels. So with usage basically of 7 bits, we can express 256 values. And then with INT4, it gives us only 3 bits. So it's 16. Why 16? Because we also have the sign that we need to remember. So this is the red one. And now let's look at some examples to better understand it, because if you see it, then for you, it's even after example, it looks still probably like dark magic. Okay. So as we can see here, we have the float 16 example here with the same value. As we can see, the exponent and significance are different. We can, of course, play with it to understand it. I also don't do the full range. So for example, here we can see how the value will be changing, but it will take a lot of time. So we'll just go like this. So as we can see, the more full bits we fill, then the closer we are to the full model. So as we said, the most important values are in the small range around 0. So that's why using float 16 will solve us half of the theorem. And here we have example of float 16. So this is format created by Google Brain, and it have 8 exponents and 7 significants. So as we can see, we can again change the values here, but it's a bit different representation, and why they use it, because they find out that it will work better for training LLMs to have bigger range, but of course with a bit lower precision. And then this allows to basically not overflow the model, because let's say we go like this over the model. So then we have known number, which basically will provide error that will propagate through the training and crash our full pipe. And as you can see, we can get it on low and big values too. Then we have also float 8 and float 4. And as you can see, there is much less values here. We can go negative to positive, and that's the float 8. And again, we can represent a bit more here, as we can see, but we can also overflow the model. So we need to be very careful. So now why it's so important? Let's look why almost every weight lies near zero. So as we count the parameters of real models, they start to pile up around zero, as we described before, and there are sometimes outliers. Outliers are very important because actually the researchers find out that having them will make the models generalize much better. So it's not something that we should cut out, because we are cutting out very important knowledge. Yeah. And then like in a data science, yeah, for you, the most important cases are the ones that are sparse or like having different values. Yeah. And here we see that's the summary. Yeah? So low precision formats are most accurate near zero, and that's exactly where the weights are. So that's why we use these formats to save. We can look here. That is nice graph to show us the precision. So we have different flows approximating sinus function. And as we can see, maybe let's start from the biggest ones. So the float 32, that's the highest precision. And if we look like this, they would look similar, but if we make a zoom, actually let's do 200, then we see that float 16 can represent some values, so we have these jumps. Now let's add to this bfloat 16. So as you can see here, we have the error value also. So as we can see, if we want to represent some value on the bfloat, the error will be higher than on float 32, and the error is minimal on float 16. And then we can add these two. And why we don't see them? Well, because the error is so big that we need to basically zoom out. The error is like 1%, 2%, and then for float 4 much bigger. And now if we jump to this, we can see that the error could be over 20% on float 4. So that's why there is specific tricks that we described in last video that, for example, in NVIDIA NV4 use to quantize the model, but also use tricks to don't have as big error values. So you can check it down below. So as I said, we save memory, but how much we save? So this is example per billion parameters before the overhead, because there are also other things. So if we jump from FP32 to, for example, INT4, so we save 3.5 gigabytes of VRAM. So as we see, each time we divide it by 2. But yeah, there is catch up, because as we saw on the distribution graph, each time that we lower the precision, then we can represent every value. So basically we get speed and lower memory, but there is more chance to have error. So the main point is to find out how to optimize. Now let's jump to the next part. The mechanics. What quantization actually does. So it's controlled rounding. And here is the full idea in one move. If at full precision, a weight can sit anywhere on this line. We quantize it, and only these notches survive. So as we can see, the value was at full precision, and because we can't represent it exactly, it goes here, and this is then our error. So as we can see, we then choose the closest representation and we get error. So that little distance, the error I mentioned, is quantization error. So it's tiny on one weight, but if we multiply it across billions, it quickly adds up. So that's all quantization is. It's controlled rounding of the numbers. And the entire art is choosing the notches that will hurt us the least. Now we'll jump to the few better examples to visualize it more, so we get a good feeling about it. So here we have better example with bfloat 16, float 8, and float 4. So now if we go, we can see it will switch to the closest value. And in float 4, we don't have that many. And as we can see, the more interesting part is that it's much more dense here in this range. So this is the range that we want the parameters, and most of them will be there. So we want to have good precision in here. It's around 0, and in float 8, you can also see that the density increased just in this specific point. Now let's look about quantization by rounding that I mentioned. So as we saw it before, we can increase this value and the weight and output change. So this is in bfloat16. So we get half. Now let's do float 8. As we can see, we lose some value. Why? Because we can't represent the exact numbers. So if you look closely here, we have minus 0.88. And if I switch it, it's 89. Yeah. So it's a small change, but it influences layer here, as we can see, by quite a lot. So that's why it adds up quickly. And here we can look at the flow. So that's pretty bad. Yeah. And as we can see, I play with this and we get 0 in the full range. Why? Because as we have here, the range of values is very small. So we can't represent these values basically in this range. And this will be now in the next visualization on this block. So here we are. And as we can see, most of the values that are there are in the range that will be 0. And only this is close to -1. So as we can see now here, that's why this become -1. And then here we have -0.54, so it become -0.5. Yeah, but all other values become 0. So that's why we need to watch out at the quantization values. So we can perform the quantization in two ways: symmetric and asymmetric. So symmetric one centers the data on 0. So it's simple. We have just number to store the scale, and it's perfect when the data is already centered. But we see here on this example, if the data leans to positive, then we waste a lot of range. So what we then do is we can do asymmetric. So asymmetric adds a 0 point to the notches slide over to where the data actually lives. So we have less error when it's lopsided. So the cost is metadata, because symmetric stores a scale, asymmetric stores a scale and 0 point. And on giant model, even that bookkeeping keeps up. So asymmetric is shifted using 0 points, and it fits the screw data better. So as we can see, we have mostly positive, and we don't have range in negative, but we center around here. And this is the formula. But now we'll look into example step by step. So first, let's look at symmetric quantization. So here we want to scale these values, and we can do something simple like divide every value by 2. And then if we divide every value by 2, when we want to get them back, we need to then multiply to get it again. But in this case, because we divided 5 by 2, we get 2.5. But then when we run them, it will be 3, not 2.5, because that range is not possible here. So then when we dequantize it, this will be 5 will turn into 6. So this is what makes the quantization lossy, but we can apply this process to any set of value, and we just need to find the right scaling factor, and we can do it by finding the largest absolute value in our dataset and dividing it by the largest value in our quantized range. So for our parameters, it could be like this. And then this is example that the author of the blog wrote in JavaScript. But here we can go to the value. So when we apply the quantization, then we can see that the values get scaled much closer. And this is how it will look then finally visually. So we scale the values. If you remember, I will show quickly. We are scaling the values that were here in the weights. So these values, remember there was issue here. So we scale them using the symmetric quantization. And here we have the summary. So the original value was -0.89, and then the quantized was the same. So the delta, which is the difference between original and the quantized, is 0. So we have 0 error. But as we can see, in the smaller case, we start getting much more errors, and here even more. But the average error is 18%. We make the model smaller because we quantize the FP16 to FP4, and the average error is 18%, which is not that bad. And here we have an example. So if you remember, at 4-bit we get mostly 0, but now if we look into it, it dynamically changed and we don't have 0 issue. To remind you what I talk about, let's jump back. So as we see here, when we were jumping with the value, most of the weights were rounded up to 0. So that's the difference that comes from quantization, properly the two float. For now, if we look at the asymmetric quantization, so this is the old example from symmetric one. So we center around 0, but as I explained before on the slide, we can see that three values are all negative, so the range is spread. It's not directly around 0. And what we can do is to apply the asymmetric quantization that I explained before. So here is just a reminder of the author actually of the block. And then we can look at the mapping, how it will look like. So we'll use the quantize function, and to the quantize, then we just need subtraction and multiplication, like here. And as we can see, we achieve much lower error by around 10%. Now we can see the example. I will increase the bfloat value, so it's 0.49. But if we do it into 4-bit, then we can see that by jump through it will be closer to the bfloat. Maybe let's pick 1. Here we have 1, and the asymmetric one gives us 0.11. This is 0.10, so it's quite close. And now let's come back to symmetric one and see how it looks there. And as we can look here, we get 0.06 instead of 10, so it's much higher error. So there are two different things we can quantize: the weights and activations. So before we jump into it, I will just quickly look back to the graph so you understand which ones were which. As we can see here, those are the weights, the blue ones, and the activations are in the middle. And here are the weights. Now we come back to the definition. Weights are the layered numbers stored in the model. They change while the model is trained, but once training is done, they are frozen. So they will not change during inference, no matter what we type. So they allow us smaller model file, less VRAM, and the bandwidth, because of less VRAM. And then activations are the temporary numbers produced as an input flows through the model. They change every time we give different inputs on the prompt, like in ChatGPT, what is the capital of France or England, and they only exist in the mid-run. So to quantize those, we speed up the actual math, but it's harder because they are different each time, because of changing. So in VLM, you could see VA-AA or V4A4 and combination of them. So this typically means that we have, for example, VAAA is like 8-bit weights and 8-bit activations. So more speed, but quality could break faster if we are sloppy, and it's harder, because it depends on input. So we need to recalculate during inference and so on. Do people grab 100 billion parameter model, find the single biggest value and quantize everything against it? Absolutely not. Let's imagine the case when we have one monstrous outlier like here. If it will be of a value of 10 and the rest will be less than 1, then everything near 0 will collapse. So basically, when we calculate the error, it will be pretty big. We'll see the more close example than this, but the solution to fix it is to quantize the block of values. So typically it's from 32 to 256 values at a time, and each block will get its own scale. So we will try to basically contain the damage that could come from this case. And here is the example. We have the weights from before, and we added one outlier of 10. And now if we do the quantization and we'll calculate the delta, we will see that the average error exploded because we add the error to everything, and only the biggest value have low error, so the outlier. So there are two phases when we can lower the precision: the training and inference. Now, how it looks like. Training is the harder one. Why? Because we have forward pass, logs, backward propagation. Then we update million of steps and we do this loop over and over again. Also, it runs sometimes weeks, months. So if we do some error here, and we realize it at the last stage, then we lose a lot of compute and a lot of time. So historically, the training, we were doing it with FP32, then FP16, BF16, and now the newest models play with around FP8 mixed with many interesting techniques. So the inference is more forgiving because there is no learning. We just do forward pass and guess the next token. During the deployment, we can easily drop to int FP4. And historically, we were doing it with FP16, BF16, FP8, INT8, and now we are focusing more, especially on the Blackwell GPUs on the FP4. And remember, the GPUs support different precisions, so this is quite important. So, for example, if you want to use NVFP4, then you need something like Blackwell because the other architectures could not support this format, and then you will not get the gains that you expect. The most common place to shrink a model is after it's done its training. We name it post-training quantization, or PTQ. We train model once at full precision, then just convert the finish weights. So this allows us to then generate the files like so GGF, GPTQ, AWQ, the 4-bit ones. They aren't new models trained from scratch. They are just compressed copies of the main model that already exists. These allow for cheapest and no retraining models. We can push it far, though the quality can slip. So typically what we do at the quantizer calibration step, we do benchmarks and we compare it to the full trained models and we see how much precision we lost. And if you track the LLM space, you can see that even Alslot, when they designed the new GPU formats, there are some issues and they are updating the weights and so on, because this is no easy task. The other option flips the order. We can do quantization aware training, QAT. This works like this. Instead of meeting the rounding only at the end, we fake it during the training. So the model adapts while it's still running. So we have the training data, we do forward pass with full precision, but we add a fake quants with a round that will simulate the quantization already at the training step. Then we compute loss, we do the backpropagation gradient, and we repeat this during the training. So the model adapts for quantization while it's still at the learning stage. And the price for it is the training compute, and this is typically a harder method to do. We'll look at it comparison soon. And now, at current stage, the Gemma use the QAT method and it becomes very popular, and we come with diffusion and so on, which I checked in my other videos. So now we are waiting. Can we, for example, use QAT with diffusion to achieve even better local AI deployment results? So what are the gains from these techniques? We can look at this table. This is post-training, this is aware training. So the primary goal in the post-training is to have speed and simplicity. So this is easy to be done and allow us to provide many formats. And the QAT, because we need to do it at training stage. If we fail, we need to retrain. So it's harder, but we maximize the accuracy. We can see here, we can basically have a model that performs like a full size model at much lower VRAM. So this is very important techniques for local AI, but also for the deployment and serving. And as we can see, this is very high complexity. This is low. The compute cost is also low, and here is very high because we do full training run. And also we need to tune data. So this is harder. Here we just do it after. We do some calibration steps and so on. So when to use during the first step, when we have limited compute and we want good enough accuracy. And this we use when we want to basically achieve as much from the model as possible, and we want maximum possible accuracy with the quantization. Now, how we will measure after the quantization, how the accuracy was influenced. There are two ways, the perplexity and KL divergence. So perplexity is basically how surprised the model is. So we have the case when the prompt is the answer to 2 plus 2 is. And as we can see, this is the probability table, and we have the highest one, 92% for D4. So the idea is that we want to collapse the full probability distribution into single number. Why? Because then it's easy to reason about and work on it. So here, for example, we'll get a score of 1.08, and it means that the model considered there to be roughly 1.08 plausible tokens that complete the prompt. So basically the model is almost certain. So the higher the probability it gave the correct token, the lower the perplexity. Now, this is the notation, how to calculate it, but it's a bit complex, as you see. But if you want, you can play with it programmatically or in a different way. And now we'll jump to the example on the page to see how this got calculated. And as we can see, there is big change in the 2-bit format. So let's find out why. So here the author used Llama perplexity tool or using Llama CCP on Qwen 3.5 9 billion model. So the way it works is that we give reference text and then it takes a sliding window of tokens over the reference text as a prompt and uses the next token in the reference text to know what the correct token should be. And this is illustrated here. We have the prompt and then the next token. So here is the sliding window idea. We can see the prompt and the correct token. So if we go through it, we see that it don't consider all the tokens before, and this is how the tool will work. So at each step, we accumulate the value, and at the end, we will get the average. So if we move this sliding window, then we will get the end of calculation that will look like this. And our CCP use the Wikitext dataset as the reference. So the author here do the same, and it just connects to the Robert Outlier. I probably don't pronounce it correctly, but anyway. So as we can see, there is the perplexity. So it's pretty low here, and then we have a very big jump. So as we see, the quantization caused the model to become less confident in its answer. And there is issue with perplexity because it only considers the correct token in the calculations. But as we see before in the probability table, the probability of all tokens is not used, so it's hard to measure. Yeah. So that's where the next value will KL divergence, so the full picture. Here we compare the entire output distribution and the score 0 is identical. So here we have the quantized and the original, and if they will match, it will give us the 0 value. And here is the value from tests that was run at the block. And here we have the full formula with the notation that you could also follow. So to maybe summarize, it compares the entire output distribution, so the original value versus quantized across every possible next token. And perplexity was regarding the, you can see here, only correct tokens, so not the ones with the lower probability. Now let's look at the example. So here we have the KL divergence of 0, and as we can see, if we move the distribution, then the KL divergence increase, and we can also move it on the other side. So this is good visualization to understand the value and how it changes. But it's not also always working in this one direction. We can also move it, for example, like this. And as we can see, here we have 0.22. Now I will try to match it. Here we have 0, so the exact match. And then we screw it more, we will have 0.38. Now here we have another nice graph. So this is regarding the prompt. So this is regarding the prompt 2 plus 2 is, and we can see the value original versus quantized. So this is nearly perfect match. Here we have the percentage. And now if we look into 4-bit asymmetric one, then KL divergence increase, but not a lot. Here with the symmetric one, as we thought before, it should be higher, and it is. So we have the difference. And then in 2-bit, it's completely gone on the other side and not much at all. So as we see, it allows us to have better overview of how the model performs. It's a bit hard because we don't have like a maximum value. So we only understand that the higher it is, the worse it is. But it's a way to look closer than the perplexity. Now it brings us to the lineup. We have same model and 4 different ways to use it. FP16, FP8, INT8, and INT4. And for each of them, we have memory, speed, and quality. So here's the trap. The smallest model is not automatically the best. If we serve million of requests, then we will focus on speed. If we are squeezing it onto our GPU, then we will focus on memory, because if we can't run it, then it's not beneficial for us. Yeah? If we do coding or hard reasoning, then we focus on the quality, because we don't want to lose the accuracy for this demanding task. So quantization is not one button, it's choosing which corner we can afford to give up. So if you need to make a decision about which precision you want to run, you can look at triangle like this. Because models are huge and they store billions of numbers, so quantization makes those numbers cheaper to store and faster to move. So, for example, training needs precision, inference doesn't. P2K is easy to do and it's a everywhere option, but QAT buys us the higher accuracy. So we need to consider also outliers, block sizes, scales, and 0 points. So we need to decide based on these details whether it will work. And the real verdict is your benchmark and using the correct ways to benchmark it. And this is something that we'll look into the next video, and also regarding the specific quantization types and difference between them. But the video gets too long, I think. So we'll look into AWQ and so on. So we don't need from the model perfect number everywhere. We just need enough precision for the specific task that we want to do. So you can choose which corner of this triangle you will want to use. And if you guys like this video, then maybe you will also like my other benchmark video about PLM systems and the inference system. This is the first part kind of the series where I want to go into more details regarding the technicalities to like really understand all of it in visual and easy way to understand. So you can check my other videos if you like this one, and see you.